Great. So if you got no question, then let me just define the score function explicitly. So the score function, S, we usually show it by S, is going to be the gradient of log of the distribution, right? And this is a score function for any distribution, not the distribution that we learn, right? Any distribution, when you take the logarithm of the that distribution and take the gradient of that one, this is going to be score function. One thing that you should pay attention, especially those of you who had some courses on estimation or detection, don't confuse yourself with what people usually in estimation call it score. So that is informant for us here in this course. So some people call the derivative of the logarithm of the distribution with respect to the model parameter informant or score, right? And then they say, okay, we want to set this score to be 0 because we want to maximize log of the likelihood, right? So this score function that we have here is not that guy, okay? Don't confuse yourself. Here the derivative is taken with respect to argument, with respect to x. There is nothing here, so it's not necessarily a problem of learning, right? You don't necessarily have a computational model. And even if I give you a distribution, you can simply compute the score function. Everybody's cool? Right? So don't get confused with this idea. If I would never mention it, but if I really need to mention it, I would call it informant. I would call this one informant just to avoid confusion. Cool, great. Now let's just look at one example. So say I have the Gaussian distribution, okay? I have this distribution. I want to compute this score function. How can I do it? What is the score function? Can you tell me? Take the derivative of logarithm, right? What it should be? What is the logarithm of the distribution? It's going to be log of this exponential term, which is minus x squared half, minus the other constant, right? Once you take the derivative with respect to the argument, which is x, that constant is going to disappear, right? The only thing that remains is the derivative of the exponent, right? Which is going to be minus x, right? So you can simply write down in this form. You could say, okay, log of px is log of this guy, and then you have a constant here. This guy is going to disappear after derivative. This is only the exponent remained here. So it's going to be minus half x squared. And you take the derivative, it's going to be minus x. Everybody sees it? Right? Clear? Easy, right? Now, one thing. This guy, the score function, is it deterministic or random? It's not deterministic. It's random because x itself is random, right? X is distributed by px, right? So the score function is also at which point you are computing? At a sample point, right? So it's not a fixed number, right? It could be like if you have a dummy distribution, but not for every distribution, right? So one thing is that the score function itself is a random variable, assuming that x is distributed with distribution px, which is the assumption when you are computing. And the other thing is that looking at this guy, if you compute the expectation and variance, what are they? The expectation is going to be the expectation of x, right? Expectation of the score function is minus expectation of x. And looking at this distribution, the expectation is 0, right? Everybody's following? Is it clear or not? Okay. So this guy is 0 mean unit variance, right? Correct? So its mean is 0. So the mean of Sx is the mean of this minus x, which is 0. The variance of this guy is going to be 1. Everybody's cool? If you don't see it, you just tell me. I can show it. Huh? So these properties that I'm showing here, especially this guy, this is not happening only in this example. It's pretty much all the time. Okay? So score function has a bunch of good properties. And I'm going to show them here. And trust me, I am not trying to just be tough and give too much details. I'm trying to tell them because then later when you want to understand the score matching idea, this is a good thing to know. I mean, that's going to make the life easier when we are studying that. Okay? So there are a bunch of properties. One nice property, which we already have used it in the energy-based models, is the idea that it's actually not depending on the normalization. Meaning that you can always compute the score function up to a constant scaling. So if I normalize my distribution by anything, which is not a function of x itself, then it's not going to change the score function, right? So you simply here by just considering one interesting case. So say that I have the joint distribution of x and y. So I do know what is the joint distribution of x and y, but what I want to compute is the score function of the conditional distribution p of x given y. Everybody's clear? So I have the joint distribution. We had it a couple of times in our course that we had the joint distribution, and then we wanted to compute the conditional distribution. Now, if I want to compute the conditional distribution of x given y, how can I write it down in terms of the joint distribution? Px and y divided by p of y. Great. Now, how can I compute p of y? Marginalization on x, right? So it's going to be summation on x, x, and y, right? Correct? This is p of y. Right? Now, if I want to compute this conditional distribution, I'm not working with a score function, I'm working with a distribution. If I want to compute this conditional distribution, I need to solve this marginalization, right? I need to compute this. And if x is crazy large, then this is going to be a very hard job, right? But what if I want to compute the score function of this guy? If I want to compute the score function of the conditional distribution, this is going to be the gradient of the logarithm p of x and y divided by py, right? Now, if I take the derivative, does py remain here? No, because this is going to be, log of p x and y divided by py. I can simply remove py from here, and then I write it minus logarithm of py, right? Now you compute the gradient of this guy with respect to x. This is something. Gradient of this guy with respect to x is 0, right? So the gradient of this second term is going to be 0. So this term is equivalent to the gradient of the joint. The score function computed from the joint distribution, right? Everybody's clear? So this can make a lot. If I need to work with the score function, this is going to make my life much easier, right? I don't need to do marginalization. And this is one key property. This is the same thing we used when we were doing energy-based sampling, right? Because there we didn't want the partition function. That was a constant, a kind of normalization. We didn't want it, right? So this is one key factor about the score function. The other thing is that the mean value of this score function is 0 most of the time, unless your distribution is something crazy. So how can I show this? Just to make sure that I'm not lying, but trust me, it's not only to make sure, because once we do it, then you get the feeling later when we are driving the score risk, this is going to be much easier. Say I want to just compute the expectation of the score function. The thing that I'm going to do, I am going to replay, first write down the definition of the expectation. So a score function is going to sit here, multiply with the distribution px, and then I have here dx, right? Now, I am going to replace the gradient, the score function with this definition. So it's gradient of the logarithm of px times px. what is gradient of log of p times p? We have done it a couple of times. What is gradient of logarithm of function f? How can I write it? It's going to be gradient of f divided by the function itself, right? Correct? Now, gradient times the function is gradient of log times the function is gradient of the term itself, right? So I can write down the gradient of log to be gradient of px divided by px, then it gets multiplied by px. This is going to be, these two are going to cancel, right? So the only thing that remains is the integral of the gradient of px, right? Everybody's clear? Questions? Now, what is the integral of gradient of p? It's not, that constant is 0, that's right. But first of all, one question. Can I say the gradient, the integral of the gradient of p is p? The integral of derivative of p is p, right? Can I say it for the gradient? Careful. This guy, this is important. This guy is not a number, right? This is a vector, right? So it's going to contain the partial derivatives, right? So for every single of them, you can say something, but for all of them together, you cannot say it at once, right? So don't do this mistake, say that, okay, this is the integral of a derivative, so it's going to be the guy itself. Because p itself is a scalar function, right? But the gradient is a vector, correct? So it's a vector of all partial derivatives, right? Now what I'm going to do, I'm going to look at one single entry in this gradient. One single entry inside the gradient, how does it look like? So one single entry here, let's just push it a bit up. So the gradient of px, when you are taking it with respect, px with respect to argument, this is going to be the partial derivative of px with respect to x1, right? The partial derivative of px with respect to x2, and so on, right? Now I'm going to focus on one of these guys. When I say the integral of this gradient, this means that the integral goes on the first one, the integral goes on the second one till the last one, right? Everybody's clear? Right? Now, if you think about the gradient, one of those entries, it's going to be one partial derivative of px, say partial derivative with respect to xi, integrated over dx, right? Now, this x is going to be x1, x2 till xd, right? And say that I'm talking about the partial derivative of px at x1. What's going to happen? So let me just do it once on the board for you, and then hopefully you're going to see the others clearly. So I am talking about this guy. So this is p of, my x is a d-dimensional thing, right? So it's going to be px1, px2, and so on till xd, right? This is my px. Everybody's clear? So I'm computing the partial derivative with respect to x1, and then I integrate it with respect to dx. What is dx when I have a multidimensional vector here? What is dx? dx1 times dx2 times dx3, so on, right? This is the hypercube, right? Tiny hypercube in the d-dimensional space. So this is dx1, dx2 till dxd, right? Okay, not very good notation, but this d is not that, right? Everybody's clear? So this is the integral that I am trying to compute here. Okay? Now, I have the gradient, the derivative here with respect to x1, right? And this integral is going over all of those guys. This means that this integral is going over x1. The other integral goes over x2, and so on till xd, right? And I assume right now that all of these x's are from minus infinity to plus infinity, right? All this space. So minus infinity to plus infinity, so on till here, right? So I am not going to do any of this. I'm not going to take the derivative yet, okay? And I'm going to keep this x1 here. So I don't have, yeah, I have a good, I have another color. So I'm going to keep this integral and this derivative for now untouched, right? Now, if I take the integral of this guy over last entry, dxd, with respect to xd, what's going to happen? If I compute the integral of px1 and x2 over x2, what do I compute? It's marginalization. It's going to be px1. So if I compute integral of this guy with respect to dxd, right? The thing that is going to happen, I am marginalizing this one over xd. What happens? Great. I'm going to drop it, right? Everybody's following? Now I go for the next one, dxd minus 1. I'm going to drop that guy, right? I keep on going till I get to x2. I still have, so this integral is going to disappear, and so on. I get to x2, right? Then when I take the integral of this one, which is only now x1 and x2, over x2, this is going to disappear, x2 is going to disappear, and this guy is going to disappear, right? So I'm going to remain by the distribution of the first entry x1, dx1. Now I have the derivative. Now I'm taking the integral. What is this guy? Okay? I have a function f. This is, I am computing this one. What is this integral? Can you tell me? F prime x times dx integral. How you compute this? FB minus FA, right? Principal theorem of calculus, right? So this is FB minus FA, correct? Now, this is the same thing here, right? You have the derivative of px1, dx1. You're computing it from minus infinity to plus infinity. What would it be? It would be px1. Once computed at plus infinity, once computed at minus infinity, and then you subtract them. Everybody got the idea? Yeah? So this integral is essentially p of that xi, once computed at plus infinity, once at minus infinity. Yeah? Now, think of pxi to be Gaussian. If you compute it at plus and minus infinity, what would be the difference? 0, right? Any distribution, which is a kind of well-defined distribution, it's going to vanish to 0 at some point, right? It cannot keep up forever, right? Then it's not going to add up to 1, right? So any well-defined distribution is going to be decaying, and this guy is going to be 0. Everybody's cool? So the score function, when you compute the expectation, this expectation is going to be 0. Okay? Any questions? No question? Okay, great. So if you got no question, and I really, trust me, I did not want to just take you through basic integration. This is because we're going to do the same thing later with more mess when we get into the score matching. So I just wanted you to get the idea right here before we get there. Okay? Trust me, I'm not the bad guy. Okay. Now, the next property is the fact that, typo, so this guy, this should be about the covariance, right? So the title here is wrong. Yeah, this is what happens when you copy and paste very fast, right? So the second property is that if you compute the covariance matrix of this score function, you're going to see that this is equivalent to the minus Jacobian of the same function. Now, I'm not really going to prove it for you because there is no benefit in doing that. I mean, this is not a very fascinating property, but just wanted to tell you that this exists, and you can simply do it by the same thing, right? You just write down the definition, you do the mess of all of those integrals, then you're going to end up with that expression. So you're going to start by the covariance definition. It's going to be the score function itself minus its expectation times the score function minus expectation transpose, right? And then you use the fact that these expectations are going to be 0. Then you're going to get rid of it, so you're going to have only this guy. And then you're going to do a bunch of same things that we did here. You end up to see that this expression is essentially minus the Jacobian of the score matrix, score function, sorry. Okay? Everybody's clear? Now, if you put this one, these two, if you check these two properties for the Gaussian example that we had, you're going to see that they are satisfied. The mean is 0. The variance there was 1. Now, if you compute the Jacobian, I mean, it's just one number. It's going to be minus 1. Then minus 1 is 1, right? Yeah, you can confirm it by the example. Questions?